that we just saw. So I'm Robert Pincus. I'm a professor at Columbia University at this Lamont Doherty Earth Observatory. My claim to fame in this community is that Ryan Abernathy used to sit through that wall over there. Um, I study atmospheric radiation, so I study the flow of light that through the atmosphere. I used to work in prediction. I used to work with NOAA, and so I built as part of that this code with this terrible name, RTE and RTMGP, and I'll explain that. It's a Fortran code for computing how light energy flows through the atmosphere, the sunlight and the light from the planet. Originally, we started this project in about 2019. We started the project in 2016. The first sort of documentation and the first working release was 2019. And it's used in weather and climate models. Most of the climate models in the US use this code now. It's in for it. Well, I'll explain why. It's both Fortran and coder in quotes. That's a conglomeration, that name, and there's basically two pieces of the problem that you have to do. One of them is you are solving the radiative transfer problem. And so that means that you're specifying it in terms of the optical properties, how opaque it is, how much it reflects, what fraction it reflects, which direction the light goes. You have boundary conditions, you have the sources of radiation. And then there's this step that you have where you start from something like temperature and pressure and humidity in the presence of clouds, and you turn that description into a radiative transfer problem. That's what RTMGP does. So you'll see the GitHub repositories for each of these things at the bottom of the pages. Okay, so this is where we started. There's two pieces that I want to cover here. One of them is that RTMGP, this mapping from the description of the physical state of the atmosphere to the radiative transfer problem you have to solve. There's tons of empirical data, what I've heard referred to as scheme data. We package that separately. It actually has its own GitHub repository. And then the code itself is separated into two different pieces. One of them is user interaction, and the other is computational kernels. And from the start, those computational kernels have had C bindings. So the user interaction does data sanitization. It does, it just presents a nice way. One of the things it does is it provides in Fortran the kinds of things that Xarray does in Python in a more rational language. Okay, so it's always been designed to be plug and play. So we have actually C++ front ends. My code originally was written in Fortran. We have C++ front ends. We have CUDA back ends. It was always meant to be mix and match with languages. And because this is a calculation that lots of people want to do, not just in order to run their climate model, but in order to understand things about the Earth, we really wanted to make this available offline. And of course, that sort of implies to me Python. So I managed to scrape together some money, hire MakePath, and so Brendan Collins on the call, to build an initial version of this Python front end RTE. So it is a Python, and I sort of stress Pythonic interface to the Fortran kernel. So users are using the same underlying code and the same underlying data that the weather prediction or the climate models are using, but they're doing it in Fortran in the kind of Pangeo ecosystem. We follow Xarray conventions. And in our case, we have sort of specific data arrays. That's how we do that. And it's parallelized with Dask. I'm just going to show you two quick examples. Again, apologize for the terrible visuals. We initialize, we load the scheme data in this first line, right? Where we instantiate a new, so pyRTMGP uses a class, a straight up Python class. We initialize it with data. It goes and it reads the data. It stores that in Xarrays, but those things are internal. You can then go out and collect. In this case, I'm showing you reading data from a file, but that atmosphere data, it contains profiles of gas concentrations, temperature, pressure, these kinds of things. And then you compute what we call the optical properties. That's this step, this last line maps the physical description to the optical description that we need to solve the radiative transfer problem. So the point is really just that we have this step that does the translation that relies on data that we package and which users have different options for. And this produces an Xarray data set that has the data arrays that we need to solve the radiative transfer problem. And then pyRTE uses an Xarray accessor. And we do that for composability. So essentially, what you do is you take the X-array data set that has the description of the optical properties, and you call RTE solve on it. And that you can either add to the original data set, or you can do it separately, which is what I'm doing here. The reason that we do so for the LW long wave, that's the terrestrial radiation. You can also do it, and you can either for the short wave or the long wave, the LW or the SW, you can just compose. So you can compute the gas optics and then use .RTE.solve directly on by using the X-array accessor, so that you're not storing intermediate results. You're just going ahead and going directly from the state of the atmosphere to the fluxes that you need. This composability extends. There's other features that the code has, for example, treating clouds that I won't bore you guys with. We've relied real heavily on the infrastructure that Pangeo has provided. So we have API documentation auto-generated that goes on Read the Docs. We have tutorials. Those come as a Jupyter book. Every time we build a new release, that Jupyter book gets on GitHub pages. We have bigger examples too that we don't run, but they live in the same tutorial directory. We're just distributing everything via Conda, and we're going to put this on pip, and we have a Slack-alike workspace for the relatively small developer community. So why am I boring you with this? This is like just a package that I made to do the kinds of problems that me and my colleagues need to do. And basically, I'm trying to nerd snipe you. I really would love some help from like software grown-ups, because I'm a professor. This is not my day job, and I'm also terrible at it, to be quite frank. And so it's mature enough. People are using it. That community is growing. It's a very valuable piece of software in my narrow little world. And so I'd love to solicit some help. And there's some interesting, I think, software problems here. We're doing broadcasting, but we're not doing it in, I think, maybe the optimal way. There's a difference there's a little bit of a conflict in the parallelization. We're using Dask to provide chunks, but the Fortran kernels underneath actually expect already chunks, and they are optimal at much smaller sizes. So we'd like to think a little more systematically about how we do the parallelization. I have GPU kernels that work with OpenACC and Fortran, and I would love to be able to figure out a way to use QPy or some other way of exploiting GPU hardware when it's available from Fortran. We'd like to do data validation, and I need a new logo. And so if you have bandwidth and this project looks interesting, please let me know. I'd love your help. Thank you.